Hello and welcome, Putnam High School physics class, to yet another edition of As the Putnam World, Physics World Turns. I invite you to come into my home today, into my home office, so that I could teach you a little bit about work and power. You'll recall in our last video, we've talked about energy and the different types of energy, mainly being those of kinetic and potential energy, specifically gravitational potential energy. Well, today, we are going to continue on with our discussion of work and power. So, I will be using my purple marker now that I found in the last edition. And let's start with what we know. All right, so work. What exactly is work? What is work? Oh, that's pretty good. Okay, what is work? Well, work specifically is a force that is exerted on an object over a displacement, okay? A force that is exerted on an object over a displacement. So what specifically does that mean? I think I'm gonna go back to the black marker. Ooh, maybe I'll try the brown one. So what specifically does that mean? Well, that's our question, and that is what we are looking for. That means we are applying some type of force over a distance. Now, you know force is newtons, correct? Makes sense. But we're applying some type of force over a distance. Okay, a displacement, right? A change from our initial position to our final position. So, let's take a little look here. Work, another equation, work is going to be equal to, we're going to jump right into this equation, force times distance. Okay, force times distance. So we can actually throw that up here. Work equals FD. Now I know you've seen that before. In fact, we've looked at that kind of force and distance when we talked about energy in the previous video. Okay, so I want you to remember that. That was actually one of our energy equations for kinetic energy and potential energy. So work is actually related to energy. Okay, so we're going to get into that in just a second. So this is measured as a Newton. This is measured as a meter. So that would let us know that work is a Newton meter. And guess what a Newton meter is? It is a joule, which we know is abbreviated as J. What other measurement also has the units of joule? And you're correct, energy. So energy is also measured in joule. So if work is measured in joules and energy is measured in joules, these two have some type of relationship as well. And that's going to be a very important relationship because it will allow us to make some important connections. Think about me taking this calculator and raising it up. Well, from here to here, I've just given it potential energy, right? Let's say this is 0 height. This is now 0.5 meter. I've just given it potential energy to 0.5 meters. But what did I have to do in order to get it from here to here? I had to exert a force pushing it up against gravity over a certain distance, 0.5 meters. So I just exerted a force over a distance. I did work to give it gravitational potential energy. So in this case, the work that I exerted moving it up is the energy it now possesses. So in essence, what I'm trying to say here is that these two are the same. Okay, so if you thought our last little unit on impulse and momentum was kind of funky in that we were asking the same question different ways, this is going to be the same idea. We're going to be asking very similar questions or going for very similar answers, but we're asking those questions in different ways. Okay, guys? So let's get a couple more notes on work, and then we will go from there. Excuse me. Remember, excuse me. All right. So let's see. What is the deal with work? Work is an application of force. So work is an application of force. It is a movement of an object by a force. Movement of an object by a force. What else? It is also, is negative work possible? And the answer is yes. Negative work is possible. Negative work is possible. And that is known as friction. It's a force opposing motion. And we have two categories of work. And those are work that's done against another force. And that's kind of like me lifting up something against gravity. And then we also, that's another, right? Work done against another force. And then we also have work done to change the speed of an object. Work done to change the speed of an object. And that could either be to speed it up or slow it down, either way. All right, so that is what work is. So the big thing to take away from this is work is equals to a force times a distance or a displacement. And work is also the same thing as energy. All right, so we've got energy. We've got kinetic and potential, gravitational. We've got work. The last thing we're going to get into before we talk about conservation of energy is actually power. Okay, so work, energy, and power. So let's talk a little bit about power because our knowledge of work is going to bring us right into power. So first I ask you, what is power? Close, close. It's a good idea though, good idea. So power. Excuse me. Power is work done over a period. Work done over a period of time. Work done over a period of time. Okay, how fast work is being done. So think about this. If I can lift a 5-kilogram block up 10 flights of stairs in a minute, and you can lift a 5-kilogram block up 10 flights of stairs in half a minute, who has the greater power? The answer is you, because you did it quicker, right? You did the same amount of work, exerted the same amount of energy, but in less time. So your power is greater, right? You're stronger, right? Okay. So power is really equal to work divided by time. And if we look at our units, this is in the joule over the second. And what this equals, it's going to be a very familiar term. It's watts. Okay. Watts are you talking about, Mr. F? Oh, you guys kill me. You really do. You're hilarious. I'm just kidding. The real unit is watts. Okay. So 1 watt of power is when 1 joule of work is done in 1 second. 1 watt of power is when 1 joule of work is done in 1 second. Okay, so now we have our 3 equations. Power equals work over time. Boom, right there. Our 3 very important equations. Okay, guys? So, one other little part today that I'd like to go over is, let's see. Well, let me do two little practice problems here, one with work and one with power. So let's say that an object is being lifted, right? So an object is lifted up to the 2nd floor. So an object is lifted up towards the 2nd floor, and that 2nd floor is 10 meters high. And the object has a mass of, I don't know, 2 kilograms. Find the work that was done to lift that object up. Well, work in this case, right, is equal to the amount of energy done to lift this up. So work here would be equal to GPE. Remember, I told you work and energy are similar. They're essentially the same thing, right? So mgh 2 times 9.8 times 10. So that would allow us to be 196 joules. Okay, so that's one way to do this problem. Let's look at a different problem that uses the FD equation. Okay, so this is very important. I want you to remember that work and energy are essentially the same thing. We could use them to calculate one another. Now let's say you're pushing a car, okay? So here's our car. You're pushing a car this direction, 20 meters down the road, and you're exerting a force of 500 newtons. What's the work that you're doing? Work is equal to FD, 500 times 20. So 500 times 20, 5 times 2 is 10. Tack on the 3 zeros, 10,000 joules. That is your work. Okay, so 2 different ways to approach a work problem. Now let's do power. So what is the power if you pushed this car, 500 newtons of force, down a 20-meter road in 20 seconds? Well, power equals work divided by time. So 10,000 divided by 20. And this gives us 500 watts. Okay. Excuse me. Now let's say, well, your friend came along and he pushed that same car 20 meters, 500 newtons of force, but he did it in 15 seconds. What's his power? Well, power equals the work done, 10,000 joules over 15. So we're going to take that and we're going to divide it by the 15, and his is 666. Whoa. All right, 666.7 watts. So he did it in less time. Intuitively, that means he's stronger, he's more powerful, right? The numbers support it. So that right there is power and work in a nutshell. Okay, there's one more thing I'd like to talk to you about today, and that is the law of conservation of energy, with one quick example at the very end, and that will be it for this video. Okay, guys? Hope these videos are helping you guys to kind of see what's going on and maybe bring a little bit of school back into your living room or your kitchen or wherever you're watching these videos. Okay, and hey, invite your parents, invite your siblings. You know, make it a party, make it a physics party, right? Make it a, you know, hey, it's physics hour with Fabs. Yeah, get the popcorn, get the chips. Watch a movie? No, watch a Fabs. All right, guys, one more, then I promise I'll let you go. So we are going to talk about law of conservation of energy. Conservation of energy, guys. Here we go. All right. Anytime you have a law of conservation of blah, it's always blah can never be created or destroyed, only transferred or transformed from state to state. Same thing here. Energy cannot be created nor destroyed. Here's a long one. Energy cannot be created or destroyed. Okay? It can only be transformed. It can only be transformed from one form to another. From one form into another, but the total, very important, but the total amount of energy never changes. So, pause this if you need to. Write this down. Very important. Energy is never created nor destroyed. Never, never, never. It's transformed from state to state, kinetic to potential, potential to kinetic, right? But it's never, ever, ever, the total amount never, ever, ever changes. So pause this, do whatever you need to do. Make sure you get this down. Okay, so we had that in word form. Now let's put that into equation form. So the energy total before equals the energy total after. Okay? How many different types of energies have we talked about thus far? Correct. 2. We've talked about kinetic and potential. So those are the ones we're going to use. So all of the PE, right, potential energy, gravitational, initially, plus all the KE, kinetic, initially, right, I's, equals all the PE, final, at the end, plus all the KE, final. Now, does that make sense to you? All your energy before, which is PE and KE, must equal all of the energy after, which is your PE and KE after. Remember, you're not gaining or losing, it's just changing form. And you actually already kind of did this a little bit when you looked at the roller coaster equation from the previous worksheet. So let me do a little problem, and then we will call this video a wrap. We'll produce it, we'll get it out on the airways, and that will be it. So I am going to remember this equation, then I'm going to show you guys a problem that I'll be reading, and I would really like you guys to pause this, read through it. Okay, so take a read on this problem. I will read it to you as I am showing it to you. Okay, so let's see, there we go. Mr. F is riding his wagon down the hill that is 10 meters tall. His mass and the wagon's mass are 40 kilograms. And he is traveling at a velocity of 0.5 meters per second. Assuming that there is no friction, very important, no friction, how fast will he be traveling when his height is only 1 meter? Okay, when his height is only 1 meter. So let's take a look at this. So essentially what's happening is, here is my wagon. Here is me. There's my here, right? And my smile. And I am traveling down this hill. And here I am 10 meters high, right? Yeah, and I'm traveling at 0.5 meters per second. And here's the ground. But the most important part here is at 1 meter high. I want to know what will be my velocity here. Not at the ground. I want to know what it is at 1 meter high. So pause this, write this down if you need to, because I'm going to use the whole board. So let's plug it into our law of conservation equation. Okay. So all the energy total before must equal all the energy total final. Okay. So energies are PEs and KEs. So PE initially plus KE initially equals PE final plus KE final. Let's just kind of put in all of our equations right now so it makes life easy. mgh plus 1/2 mv squared equals mgh plus 1/2 mv squared. They're just the GPE and the KE equations. So we've really done nothing too crazy yet. All we've done so far is just replace variables with equations. Let's plug it in, okay? The mass of myself in the cart, 40. Gravity, 9.8. My original height, 10 meters, plus 1/2 constant. My mass again, 40, times my initial velocity, which is 0.5, and we square it, equals, did my mass of myself in the cart change? No. So it's still 40. My gravity, 9.8. My new height, very important, 1. Plus 1/2 constant, my mass, times my velocity squared, and that is the velocity that we are looking for. Okay, let's keep moving on. Multiply all this out, we get 3,920 plus, make sure you square the 0.5 first, multiply by 40, multiply by 1/2, you get 5 equals, multiply all this out, you get 392 plus 20 v squared. Add these two together, you get 3,925 equals 392 plus 20 v squared. Let's subtract this over. And we get 3,533, 3,533, and that equals 20 v squared. What do we do now? Very good, we divide. And we get 176.65, 176.65 equals v squared. What do we do now? Excellent job, we square root. And we find out that, we're gonna write this, I'll write it right over here. V, my velocity at 1 meter high will be 13 0.3 meters per second. And that's it. Some important things to remember. This right here was a total amount of energy that I started with. It will never ever change. Okay? 3,925. That total energy will never change no matter where I am on this slope. Whether I'm 1 meter up, 2 meters up, 3 meters up, 9 meters up, 10 meters up. That energy will never ever change. As I start to go down the hill, though, my kinetic energy will take a larger percentage because I'm losing height. And my potential energy will fall in numbers. Okay? So if you look, way up here at 10 meters high, I had a potential energy of 3,920. But down here at 1 meter, it was just 392. Okay? So, need to understand, with conservation of energy, as you lose height, you gain velocity in most cases, and that takes your percentages and changes them from less GPE to more KE. Okay? So please email me with any questions, guys. I'm definitely here to help you guys. We can do Zoom meetings, we can do whatever you need. But make sure you're practicing on these. Make sure you're emailing me with any questions. If you need anything, please don't hesitate to let me know. All right, guys, have a great day, and I will see you all in the next video. Take care, guys. Bye. I really need to work on some cool like entry or like some way, like, you know, if I could make myself like fly away, that'd be awesome. But anyway, just ideas. See you guys. Bye.